guys, listen up. We did an exam what I'm planning for this week is that we're going to get almost done in material today. Probably not finished in 2 weeks, but I'm planning to not have class on Wednesday. Okay, so this one? Right, it's coming Wednesday. We might not finish all the material today, but I'm going to do a screencast. We're going to catch the very end of it. It's pretty simple anyway. And today we're going to finish up those simple circuits that we started. Remember we were doing the EMF, the alternating EMF, the resistor alternating EMF. Inductor, I think we did last. I know we did it with capacitor. Today we'll do it with an inductor, and then also today we'll put all three together. We probably won't get the transformer, but we've seen transformers before. It's just, and so I'll put together like a screencast on YouTube, and you'll put markers like between now and then, between now and Friday. And then on Friday we'll come back together and we'll have a review for the test. But I don't think we really have enough material to warrant 2 days of class. 2 extra days of class. That's okay, no class. Okay with that? I don't think they're And I know we haven't had any clicker questions, but I will take a look at the clicker points and see sort of where y'all stand. Many of you already have exceeded your 50 points, but I might also provide another opportunity for that. To pick up if you're not quite there, to pick up some extra points for your class participants. So I'll send y'all an email regarding that if it affects you. It doesn't affect you. I'll let you know. I'll send this all out in an email later today, but we'll go and plan on no class Wednesday. All right? You have a good weekend? Yeah? All right. Well, let's see. We left off, and I did send you some homework, and you have some sample problems where you're dealing with some of these simple circuits. So you can certainly see, and you will see, one or more of these simple circuits. So here we were dealing with a capacitor. The capacitor, the voltage follows the voltage of the EMF source. That's that DC sine omega dt. And then so we can find our charge in this way on the capacitor. We can take the derivative of that, which is our current, the derivative of the charge. We get a function that's a cosine function. So, and here we also define the capacitive reactance, which is this expression. This is sort of like the resistance. We'll see that it's very similar. Because if you look at this, this is our current right here. Remember Ohm's law? Our current is V over R, right, for Ohm's law. So what we're doing here is we're defining our capacitance in terms of this Ohm's law. So you can think of this, this X, capacitive reactance is sort of like resistance. Y'all follow what I mean by that? Because if we have Ohm's law, which is V equals IR, then I is equal to V over R, which is what we have here. I is equal to V over this capacitive reactance. Right? So it's just sort of redefining that and how does, and asking the question of how does the capacitance of this circuit, how does it impede the current? So it's not exactly resistance, because remember capacitors, they don't have current flowing across them because they're just two parallel plates. There's no charges that go across them unless they're broken. So it's not exactly the same as resistance because it doesn't resist the flow of electricity, but it acts in the same way. So this will come up again soon when we deal with RLC circuits. All right, now if we were to plot these two functions, I have the voltage of the capacitor given by this function, and then the current of the capacitor given by this function. One's a sine, one's a cosine. So I'm going to go to this next page. So I had VC equals the magnitude sine omega dt. And then I also had I, see that's the current on this capacitive circuit, equals to what are we calling it? VC over XC cosine of omega dt. Remember that omega d? What is omega d? What does the d stand for? It's the frequency of what? Omega d. The angular frequency of what? Sort of. Phase and your angular frequency are a little bit different, but omega d is the driving frequency, and that's the frequency of what then? It's the driving frequency as opposed to the natural frequency of your circuit. No? Okay. All right, that's fine. So omega d, that's our driving frequency. That's our frequency of our source. That's what's coming out of the wall, right? So we drive our circuit at this frequency. That's different from our natural frequency, like in our Rlc circuit where we naturally went back and forth at a certain frequency based on the value of the inductance and the capacitance. All right. Anyway, so if we were to plot these two, a sine and a cosine function, how much are they out of phase, a sine and a cosine function? Oh, right, by not quite a half a wavelength, by a quarter, right, by a quarter wavelength, by pi over 2, right, because if I think about it, it goes 0, pi over 2, pi, 3 pi over 2, 2 pi. So anyway, if I were to plot these functions, my v function, I'll do in black here, starts here because the sine of 0 is 0, and it's going to look like this. And my I function, cosine of 0 is 1, so it's going to start right here. And it's going to look like this. Be prepared, you might have to sketch out some of these functions for your exam. Or, as I gave you a problem in the new homework, you'll have to sketch out the phasers. You'll definitely have to sketch out the phasers for certain functions. So if I were to sketch out the phasers here for this function, let's say that I just pick a point. Say I want to pick this point on this function. And I want to draw the phasers for these two graphs. All right, first I'm going to draw the phasor for the blue line. So we'll do this down here. For the blue line, the current, remember the y component of the phasor gives the magnitude. So I know then, since the y component of this phasor gives the magnitude, my phasor for current, the blue line, is going to be in one of what two quadrants? Because the y component has to be positive. So it's going to be in either quadrant 1 or what? Either 1 or 4, right? Either here, or no, not 1 or 4, 1 or 2 or 9. Yeah. So my y component has to be a positive value, and it has to be a positive decreasing value. Now remember our phasors, they go in this direction at a rate of omega dt. Right? So what quadrant is my phasor for the blue line? That's my current here. What quadrant is it going to go in? I think it is 2, yeah. All right, yeah. So my my phasor for the blue line is going to go here. Let me write it in blue, bless you. That's my current. And then what about the black line? Its y component is also positive. All right, so it's either going to go in 1 or 2. Which quadrant will it go in? It's going to go in 1 because it's increasing. Remember, as my phasor moves towards this quadrant, the magnitude increases because the y component gets bigger. By what angle are these going to be separated? The blue line, and what I'll draw is the black line for the phasor. 90 degrees, or pi over 2, because that phase shift between them is 90 degrees. So my phasor here, this is going to be my phasor VC. And they are going to be separated by 90 degrees.
Always separated by 90 degrees?
Always separated by 90 degrees, because these two functions are always true. Since our current, how do we get these two different functions, the sine and the cosine? We did what to the voltage? Or what did we do to this function to get our current? We took the derivative, right, yeah. So that's right. So we took the derivative, so they're always a sine and a cosine, they're always separated by 90 degrees, like this. All right. Let's see. All right, let's do the third circuit, which is And then I'll do a quick little example. This simple example, but let's say that I have an AC power supply. It has 36 volts. It's connected to a 15 microfarad capacitor. Again, you had some problems like this in the homework. There's new homework problems. I'm going to send you a couple more homework problems just for extra practice. But that's going to be your go-to guide for the test, what to study for the test. Your test questions will look very similar to the homework questions. All right, so I have 36 volts, 15 microfarad. What is our voltage, our function, our voltage as a function of time, VCT, and what is the amplitude, VC. All right. I want to know what is the function here. In order to find the function, I need to find the amplitude, and I also need to find the frequency. And the frequency, our driving frequency, is just like our driving frequency in our electrical system. It's going to be 60 hertz. All right. So I first want to find omega. How is omega related to the frequency, F?
1 over the square root of Rlc.
Oh, no. If I have my frequency, how do I find my frequency? How are these two related? Remember, this is in 1 over seconds, and this is measured in radians per second. So how do I get from this to this? Right, we just multiply by 2 pi. So omega then is going to be 2 pi f. That's equal to 120 pi, because f is 60. And then I want to find VC of t. That's equal to my amplitude, my voltage across my capacitor, times the sine of 120 pi t. VC is going to equal to the amplitude of my driving source. That's that 36 volts. So I can write this function then as VC of t is equal to 36 sine of 120 pi t. Okay, so this is the function that describes the voltage across that capacitor. So if I want to find the voltage at any particular time, 1 second, 2 seconds, whatever, I can just put in my time here. And it'll tell me what is the voltage as it goes back and forth from positive to negative 36 volts. All right. Let's look at the third circuit here. And we're sort of building up to an RLC circuit where all three of these are going to come together. But our circuit number 3, we've done resistors, we've done capacitors, now we're going to do inductors. This is our inductor L. This is our EMF source, we'll call it EM. Now, just like before, the voltage across that inductor will be equal to VL times sine of omega dt. Alright, I also know that VL, just by Faraday's law, is equal to L di dt. So I can say then that di dt, if I just put these two together, is equal to VL over L sine omega dt. I want to get to a function for I. What is the current across this inductor? I know that this is true, and I know that this is true. Right? This is just my voltage across an inductor. It's equal to the inductance times the derivative of the current, how the current changes. So this is going to be my my expression for the current. So if I want to find current, I just take the integral of that. And of course, if I take the integral of a sine function, what kind of function do I get?
Like negative cosine.
Right. I get a cosine function. So I get a negative of the cosine function. So just like before, when I had a cosine and a sine function describing the voltage and the current, I'm going to have a similar thing here, where the current will not be in the same phase. It'll be 90 degrees out of phase with the voltage. So if I do this integral, my current is going to equal to negative VL. I get an omega d out of this term when I take that integral, over omega dl cosine omega dt. So that is my current function. Just like we did before, I can describe an inductive reactance. Remember with the capacitor we had it was like omega dc, or excuse me, 1 over omega dc. What is our inductive reactance going to be here for XL? Remember, I want to have it such that XL, or excuse me, that VL is equal to IL times XL. So what is my reactance going to be in this case?
No, it would be.
Yes, but I want it in terms of omega d. You're right that it's V over I, because it's sort of like a resistance, right? So what is it going to be?
XL equals 1 over omega d L.
No, but you're on the right track. All right, so I'm looking at this, right? And I want to put this in terms of, let's just write it like this. I'll say IL equals VL over XL. All right, so what is my XL going to be if I compare these two equations? What is my reactance going to be? No, you're sort of barking up the wrong tree, but Josh, you got it. It's just going to be omega dl. So I'm just comparing these two terms, and I'm trying to create a term that's sort of like resistance based on Ohm's law, and that gives me my inductive reactance. So it's just going to be omega d times L. And again, that's just like we had with the capacitor, that capacitive reactance, except now in terms of the inductor. Inductor is not really a resistor, but it does impede the current because of the way that we talked about before, that it has an EMF that opposes the actual EMF, and so it acts sort of like a resistor. It impedes the current. Right, so that's our XL. That'll come up a little bit later. Now let's draw these functions, and we can look at the phasors. So if I draw the two functions, let's see, I will draw VL in blue. Where was VL? VL is this function. It's going to look like this. And IL, I'll draw in red. IL is this function right here. And it is a cosine, but look, it's a negative cosine. So where is it going to start? It's going to start at, well, yeah, -1. Not actually -1, but negative I. The negative current. So this is my IL function. It'll look like this. All right, it's offset by a phase of what? A quarter wavelength, pi over 2, or 90 degrees. So this is I. This is V. So if I want to draw my phasors for this, let's do like we did before. I'm going to pick a point right here. Where are those phasors going to be? For the blue first, what quadrant is it going to be in?
1.
Well, let's see. It's positive, so it has to be in either 1 or 2, and it's increasing, right? So it has to be in quadrant 1. So VL is in that quadrant. And what about the red? What about my current? What quadrant is it going to be in? Now it's negative, so it's either 3 or 4.
It's gonna be 3, because it's negative and increasing still.
It's negative and going towards 0. All right. So it's going to be in quadrant 4. Imagine my phaser's here. Remember, it goes in this direction. So to be negative, it either has to be here or here. Remember, I'm looking at the y component of this vector. As it moves up, that y component goes to 0 until it gets to this point. That's right. It's also off by 90 degrees. And it's always going to be off by 90 degrees. So this is my IL. Right. And they are off by a phase shift of 90 degrees. Remember, this always goes in this direction. It rotates around. It actually rotates around at this omega d, this angular frequency. That's what that means, angular frequency. All right. All right, just bear with me. We're getting to something here, so because we're going to put all of these together. And let's go ahead and do that now. Let's look at an RLC circuit. Go with me, okay? Sorta, kinda. Okay. It's going to really come down to practicing these things, but you will have to draw some phasers for these various scenarios. And by the way, if you came in late, we're not going to have class on Wednesday. I'll send you an email out about it, but we will have class on Friday. It'll be sort of a review for the test, but I recommend that you come just to make sure that you're all on board. All right, so let's look at an RLC circuit. Have an EMF source, have a resistor, that's the R part, have an inductor, that's the L, and then I have a capacitor. My EMF drives the circuit in this way, omega dt. And I want to create a function for I. And I know the basic form for this function is going to be I sine of omega dt minus my phase shift. Okay. I also know that the current will be the same for all three of these devices, because whatever current's in the circuit is what's in the circuit. So I is the same for all three devices. For the resistor, the inductor, and the capacitor, it's going to be the same. So what I want to know is I want to know what is the current here, this I, and I also want to know phi, my phase shift. All right. If I draw my current phasor, it's going to look like this. It's going to have a magnitude I, and it's going to be offset by omega dt. Oh, I always do that. Sorry. Minus phi. That's my current phasor. And that's what I want to find. I want to find the magnitude I, and I want to find that phi, so I can characterize what is the current and find the current at any point in the circuit. But I know that the current is changing differently for all three of them, so I want to figure out in what way are they interacting to provide this final current. And we're going to do that by looking at the phasors of the voltage for each of them. May I go down from here? All right. So one of the phasors follows the current. What is that? One of the voltage phasors follows the current. What I mean by that is it's always the same as the current. Y'all remember which one it is? Is it the current, or excuse me, the voltage for the resistor, the voltage for the inductor, or the voltage for the capacitor? Which one is always in phase with the current in the circuit? No, it's okay, Josh. I'm okay. So we have three things. We have the resistor, the inductor, and the capacitor. I'll come back here in a second. And then we have the current in the circuit. One of those, the voltage in that device, the resistor, the inductor, or the capacitor, will always be in phase with the current. Which is it? What did you say?
I think it's the resistor.
Why do you think it's the resistor? You're right, but what? Okay, no, that's a good reasoning. The voltage in the resistor will always follow the current in the circuit because of the way, I mean, you change your voltage in your resistor and your current will change in the same way. If you go back and look at those functions that we had for voltage and current, they're the same functions. So they're always in phase. So my VR phasor, this is my VR phasor, it will always be at omega dt minus phi. It's always the same phase as the current. Then I want to draw my phasor for VL. Does VL precede the current, or does it lead the current? That means, would I draw a VL over here, or would I draw a VL over here? Does it lead or lag the current? VL? No, VL actually leads the current. Let's see if we go back to our inductor circuit. See, this is our current right here. Our VL always leads that current. So VL leads the current. Whatever current is in the circuit, VL will lead the current. So if I draw VL, it's going to be right here. VL, it leads the current. And the current is going to be right here. So this is going to be my I. And then what about VC? Does it lead or lag? It's going to lag. So my VC will look like this. These are all 90 degrees out of phase. So these are all 90 degree angles. All right. Now, I also want to find the EMF phasor. And it will be the vector sum of all three voltages. That's going to be VL, VR, and VC. They don't cancel, but they're not equal, so we have to take the difference in them. Alright, so when I find my EMF phasor, it's going to be equal to the sum of all of those. So I can draw them. My EMF phasor, by the way, in this case, the one that we've drawn, your EMF phasor is going to look sort of like this, and it's going to be at an angle of omega dt. So I get rid of that negative phi. It's just omega dt. Alright, because if you remember, my EMF was equal to EM sine omega dt. Okay, y'all with me on this? Is this really exciting to you? Alright, this is kind of cool actually, the way we come to this solution. So, if I want to look at phasors, I can describe this phasor. Because VL and VC are not the same, I can say it's the vector sum VL minus VC. And this phasor is VR. And so my EMF phasor is the vector sum of these. You know, where I find the Y component and the X component, and I add them up, just like we did last semester. All right, so we're just dealing with pure old vectors. So now we've taken this from these functions that are trigonometric functions, and by writing them in this phasor space and drawing them in this way, we can think about them not as oscillating functions, but as just vectors. All right, so this becomes a pretty simple vector problem. E squared then is equal to VR squared plus VL minus VC squared. We're going to let VL equal IXL and VC equals IXC. Remember, those are reactances. You'll have those expressions for X and C, XL and XC. And so E squared then is just VR squared, or excuse me, I'm sorry. me erase that, is I R squared plus IXL minus IXC squared. I'm just using Pythagorean theorem to find the component or the magnitude of those two vectors, VL minus VC and then VR. So I can find I can factor out an I squared there, and I get I is equal to E over the square root of R squared plus XL minus XC squared. Alright, this we call the impedance. How do those three things come together to impede the flow of electricity? It's the impedance. And we're going to let it equal to Z. So this whole thing will just simplify to E over Z is our current. I is just equal to the EMF over Z. Alright, we also know, we know what XL and XC are. I'll just write them here to remind you. XL, which we found previously, was omega DL, and XC is 1 over omega DC. Alright, so that's this is our maximum current. We also need to find what? If we want to know the function for the current, that's the maximum value. What also do we need to find? What, Hunter? No, we have the maximum current. We can find the maximum voltage because we know the impedance. But in order to describe that current, what else do we need for that function? We had I was equal to Im. That's this value that we just found, the maximum current, times what? What else was wrapped up in that function that we needed to know? Right. Phi. It's the same symbol we use for flux, but it's phi is the phase shift. So how much is it shifted over? It tells us the angle part. So we can do that pretty simply because it's just a vector problem. We just say the tan of phi is equal to VL minus VC over VR, and that'll give us our angle phi, which is the inverse tan of XL minus XC over R. And this is our phase shift. So if we go back, we wanted to know our function for current. I is equal to that I max times sine omega dt minus phi. So now we found this value and we found this value. So now we can tell our current at any time, at any point in time. Okay. Now there's something else that comes up here. Because remember we talked about whenever you drive a circuit, an LC circuit with an EMF source, what frequency does it follow? Does it follow the frequency of the EMF source, or does it follow that natural frequency of the circuit? It always follows the frequency of the source. Even though the two devices, the inductor and the capacitor, they have a natural frequency for switching that energy back and forth, they're always going to follow the driving frequency of the source. But there is a resonance frequency. And this is the frequency at which you'll get maximum current in the circuit. This frequency, I, EM divided by the square root of R squared plus, I'm just rewriting something here that we've already written, omega DL minus 1 over omega DC squared. Remember, this is XL, this is XC. So we've already written this, but our resonant frequency occurs when this term equals 0. And when that term equals 0, I can just say omega dL equals 1 over omega dC. I can solve for omega d. Just 1 over square root of LC. This is the resonant frequency. Which, just to remind you, I know you probably don't remember, but this is the same frequency as that natural frequency, like a natural sort of in quotes, for the LC circuit. Okay. Remember that LC circuit? It was like a mass on a spring. It oscillates at a very regular rate. Energy's going back from the inductor to the capacitor, from the magnetic field to the electric field, and it operates at this sort of natural frequency depending upon what L or C are. And that resonant frequency, when those two frequencies match, the frequency of your LC part of the circuit and the frequency of your driving source, that's going to be a resonant frequency. All right, let's see. Let's do an example, and then I'm going to put transformers on a screencast. We've done transformers before, so I don't think it'd be a big deal, but I'll put that on a screencast because I don't think we're going to get to it today. And then that'll be the last topic for the whole semester. Okay? There is, if we look at first of all, if we look at our phasers again, this might help you to remember it. Think about this. I have my EMF. The current in the source, or the current in the resistor, is always in phase with the EMF. So this will be VR. And then I also have VL and VC. There's a mnemonic to help you remember this. It's called Eli the Iceman. And this is just to tell you that for an inductor, that's L, the current lags VL. That is, my current will be right here. My current in the circuit lags VL, and for a capacitor, I'll show you how you can get this from this mnemonic. But for a capacitor, the current leads VL. You can tell that here because in an inductor, the current comes behind the voltage in the inductor, and for a capacitor, the current comes before the voltage in the capacitor. All right. So I'm not sure how helpful that mnemonic is, but that's generally the one that's taught to help remember that the voltage in the inductor leads the current, and the voltage in the capacitor lags behind the current. Is that helpful at all for you? Sort of, kind of, maybe? Just helps you to remember how those voltages, how those phasers are oriented with respect to one another. All right, let's do a quick example. And on the test, we'll talk more about this on Friday. We'll review for the test, and I'll sort of give you a rundown of what to expect for the test. But I would expect some calculations, kind of like the examples we've been doing, but then also some interpretations, drawing phasor diagrams and what have you for circuits. All right, we'll go over that on Friday some more as I get the test created. Let's do a quick example. Let's say I have an EMF source here, I have a resistor, an inductor, and a capacitor. The capacitor is 15 microfarads. The inductor is 230 millihenries, and the resistor is, let's see, what is my resistor? 200 ohms. This is my inductance. This is my capacitance. All right, I want to know what is my function for I. Oh, I also have that this is 36 volts. That's the maximum, and it operates at 60 hertz. All right, so I want to know what is I. That means I want to know what is the function. So I know that I is this I sine omega t minus phi, omega dt minus phi. So in order to find this, I want to find both what is the maximum current, I, the big capital I right here, and then I also need to know the phase shift. And then I can describe the function at any point in time. All right, so first I find omega. Omega d is 2 pi f. So that's 125, 2 pi times 60. And then I can find my, to find my maximum I, that's going to be my EMF over the impedance. Right, this is just from Ohm's law, Z over Z. Remember that Z is made up of my inductance and my capacitance. So this is going to be E over the square root of R squared plus XL minus XC squared. Turns out that XL is equal to what's omega DL, which is 86.7. This is measured in ohms. It's a lot like resistance. It has the same units. XC is 1 over omega DC, which turns out to be 177 ohms. So I can put those in, and I find that this is equal to 36 over 219, which is 0.164 amps. So this is our maximum current. Now we also need to find phi. And this just comes about from that vector analysis of the phasors. So remember, phi was that inverse tan of XL minus XC over R. I know all these values, XL, XC, R was, I think it was 200 ohms, right? So I can put those in. I find that it's negative 24.3 degrees or negative 0.424 radians. All right, and so that's it. I have a function now for my current in this RLC circuit. I know the maximum current, which is at 0.164 amps, and then I also know what is the phase shift for that function. All right, Josh?
Yeah, like XL and XC, going back to the maximum current, all you did was take what WB was, which is 125, times the value of L or the value of C.
Right, so to find XL, I said 125 times L, which was 230 millihenries. So 230 times 10 to the minus 3 henries. All right.
And then XC, the same thing, 1 over 125
times 15 times 10 to the minus 6 farads. Alrighty. There's some problems on the homework that are similar to this, but I would expect this type of thing for the test. Alright. Do y'all feel prepared for the test? I mean, I know you're not prepared, but do you feel like you know what to expect for it just yet? I feel like maybe you don't fully. The homework is a big go-to place. Like that's where you're going to have a lot of what we've been doing. For the multiple choice, you can see some of those phaser type questions. I'm not sure exactly what's on the test. Maybe that's why I feel uncertain that y'all don't know what's on the test, because I don't know fully what's on the test. Yeah, but I want y'all to go into it knowing what to be prepared of. All right?
Yeah, there's some place to be.
I understand, Courtney. But my charge to you would be just to do the homework right now and start with that. That'll be sort of where you'll be fully prepared. We've done all those problems in the homework in class, so you should be able to do them right now, but I'll have the solutions up. Hopefully today I'll have them up. I know y'all want to do them soon. Okay? Y'all feel okay not having class on Wednesday? I'll be in my office, so if you just, like, if you want to come talk to me, we can sit down for an hour and go over stuff if you're feeling left behind. But let's not meet on Wednesday. I don't think it's necessary. We do have transformers left, and I'm going to put a screencast up. We've already covered some of this in transformers, but I'm just going to recast it in terms of Faraday's law, because that's really what's going on with transformers. And I would expect a transformer type question on the test. Okay? I'll get it up today. It's not very, it's just going to be like 5 minutes probably. All right. I guess we could do it right now. Is that okay if we do it right now? It's not that long. It's not that hard, really. So, sorry. So transformers, we have 10 minutes. You know, when you're transmitting electricity over long distances, you want to have a very low current to transmit. And the reason is that our power is equal to VI, but our power is also equal to I squared R. So if I have a big current when I'm transmitting, I'm going to get a lot of power loss across your transmission lines. So when you're transmitting electricity over long distances, especially, because this resistance can build up over a very long power line, you want to have as small a current as possible so that you don't lose power. So that brings into the need for a transformer. And a transformer, if you recall, we talked about this earlier in the semester, a transformer will change your voltage, right? Step up, step down transformer. I remember that? Outside your home, takes it from about 3,000 to 120 volts. So it brings the voltage, a step down, brings the voltage down, but the current up. All right. So what you have at the power generating stations is not a step down transformer, but a step up transformer. It will take the voltage up and the current down so that the electricity can transmit over these power lines with a very low current so that you have very little loss due to the current flowing through these lines. Because you put a current through a wire, it's going to heat up. And so your power lines will heat up some, but you want to have as little loss as possible. And when you're transmitting electricity over thousands of miles or hundreds of miles, you can have a lot of loss due to just heating of the wire. And so you want to minimize that as much as possible. And so they have these transformers. They look like this. I think we watched a video earlier. Did we watch the video about how they're made? Y'all remember? I'll send it to you. We're not going to watch it here. But in short, you have, this is your power side. So this is like, you know, what's coming in your house or whatever. Although this is going to be a step up transformer, not a step down. You have this wire that comes along, and then it coils around this metal bar. This is an iron core. It's just a big chunk of metal, basically. All right, you have these wires that coil around, and then on the other side, you have wires. You have a resistor here. This is like, I don't know, the power line. And on this side, you'll have a different number of wires. So you'll have a lot more wires over here, say, for example. So a changing magnetic flux. Because the current in these wires, these solenoids, is changing. And so you have a magnetic field that's changing. And so you have a changing magnetic flux. Causes an EMF in each turn of the coils. All right, so this whole thing has a changing magnetic flux, this whole system. And that changing magnetic flux is going to cause an EMF in this coil, and 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 this coil. All of those different coils are going to have the same EMF. But because you have more coils over here than over here, where is the voltage going to be higher? On the left or right, the red or green? The green, because I have more coils that are producing the same EMF, each individual coil is producing a certain EMF, say 1 volt, I have 100 coils, I have 100 volts coming off of here. Whereas if I have 10 coils over here, I only have 10 volts, if each one is producing 1 volt. All right, so my EMF of a turn, this is the EMF of a single turn of wire, is equal to the voltage, I'm going to call this VP, the voltage across that coil, and I'll call this VS, the voltage across those turns. So the individual turns of wire will have VP over NP, or VS over NS. This is the number of turns. And on the left side, our NS is the number of turns on the right side. All right, so here, I can rewrite this to get VS. That's the output voltage of this transformer. It's going to equal, what is it, VP NS over NP. All right, so if NS is bigger than NP, is that a step up or a step down transformer?
Step up.
That's a step up transformer, right? And the reverse is true. If NP is greater than NS, that's a step down transformer. All right, so for example, let's say I want to go from 8.5 kilovolts. I want my transformer to step up from 8.5 kilovolts to 100, or not step up, I'm sorry, step down to go from this voltage to this voltage, like from the lines outside your home into your home. What kind of ratio of coils do you need? So what is the ratio of coils? Or the ratio of turns in the wire? That is, what is NP over NS equal to? So I can find NP over NS just from this expression over here. It's going to equal to VP over VS, which is going to be 8,500. That's 8.5 kilovolts over 120 volts, 71. So the ratio is 71. So if I have one turn of wire, or excuse me, if I have 71 turns of wire on this side, I'll just have one turn of wire on this side. All right, it's a pretty simple application, but it's nice, and it's only possible with AC electricity because my current is changing, and I get this changing magnetic flux. It doesn't work with DC at all because you don't get any magnetic field at all. My current is not changing. All right, guys. Okay. I'll put up your homework solutions soon and send out the equation sheet and all that business. All right, otherwise, if you want to come see me in my office on Wednesday, I'll be there. But otherwise, I'll see you on Friday, okay?